Hello, everyone. Good afternoon. My name is Pascal Fong. I'm a professor in the Electronic Computer Engineering Department. I'm also here to introduce Professor Kathleen McKeown from Computer Science Department in Columbia University as an IAS distinguished speaker on Big Data Data Science series, seminar series. Kathy has had a lot of honors, and one thing I always like to mention that she was the first woman tenure professor in the School of Engineering at Columbia University, the first woman head of department in the School of Engineering, Columbia University, and she was also the vice dean of research in the School of Engineering at Columbia University, and she's a prominent researcher in the area of computational linguistics and artificial intelligence. So she's a fellow of the Association of Advancement of Artificial Intelligence, a fellow of the Association for Computing Machinery, and also a fellow of the Association for Computational Linguistics. And among many honors, I would like to mention the fact that she is also an honoree of the Anita Borg Institute of Women of Vision in Innovations. I think that's a great accolade for Kathy. And so she is now the reason we invited her here for this seminar is that she is currently the director of the Institute of Data Science and Engineering at Columbia University, one of the biggest efforts in big data science in the United States, indeed in the world today. So without further ado, let's welcome Professor Kathleen McKeown and listen to her talk.
Right, can you hear me? Yeah, okay, good. So thank you, Pascal, for that nice introduction. Today I'm going to be talking about how we use data science in the analysis of language. And this, of course, is some of the majority of the data that is currently available on the web, large amounts of unstructured data. I'm going to be talking about a number of different applications and tasks that for which we put these approaches to use that we've developed over the years at Columbia. So data science is truly transformative. It is transforming intellectual fields. No longer do we always use the scientific method of hypothesis and test. Instead, we often use data-driven solutions. Data science is transforming our lives, for example, with areas such as precision medicine or personalized medicine, where physicians use large amounts of genomic data or clinical data in order to improve how they do patient diagnosis. And data science is also transforming business. Companies have huge amounts of data available, and they use them for marketing, for improving their marketing, or they may use data for determining how to make their investments. Columbia's Data Science Institute was formed just slightly more than 2.5 years ago. And it was formed in response to a call from the mayor of New York City, Bloomberg, at that point in time, for establishing more applied sciences hubs within the city of New York. And so Columbia responded with the Data Science Institute. We currently have 55 faculty, approximately, slightly more than that by now, actively involved in the running of the Institute. Faculty have participated from across 9 schools across campus, so it's very interdisciplinary. We have a mandate as part of our contract with the city to hire 30 faculty in the area of data science across 5 years. And to date, we've hired 15. So we're really growing. I did not include, but we do have new space, which is dedicated for the Institute, 4 floors, which we're renovating where the Institute will sit. We have also started several programs. So we have a certification in data science, which has been running. We're now in the second year. This is for working professionals who would like to move into data science. And we have a master's in data science, which we just started this past year. The master's starts off with courses in the foundations and then allows students to branch off and work in areas of interest where, so a variety of different disciplines where they might have large amounts of data and need data science techniques. And then finally, we're in the process of developing a PhD in data science, and we expect to launch it in the beginning of 2017. Our institute is formed around, you see on the far right, let's see if I can manage this. Yeah. The Center for the Foundations of Data Science. This, of course, is research that takes place in statistics, on, for example, statistical inference, in computer science, for example, in the areas of machine learning, and in general in the theory of data science. And then we have an additional 5 centers which correspond to the verticals of New York, and to a variety of different disciplines in which we're doing work. Health analytics, smart cities, new media, financial analytics, and given all of the data that we're collecting, of course, there is a need for us to keep our data safe. And so we have a Center for Cybersecurity. The mission within the Institute is to develop technology that can exploit the massive amounts of data that we're collecting to solve some of society's most challenging problems. And I've given some examples of the kinds of things we're working on that correspond to the different centers within the Institute. So for example, in smart cities, we're gathering data to monitor and protect the infrastructure, critical infrastructure like bridges that we depend on. In health analytics, using data to improve societal health and patient care. And in this talk, the work that I'm going to be talking about falls within the New Media Center. And here we're working on developing tools and talents to enhance communication and interactions within communities. So the vision of my group and my work is to be able to develop technology that can generate presentations that connect events, descriptions of events, opinions about those events, personal accounts of people who have been involved in the events and their impact on the world. And we're also looking at how we can link to supporting science. We're using a data science framework, machine learning. And what this means is we need data, which is often labeled with the outcome of whatever task we're working on. We need to be able to extract features from the data, and given that we're dealing with text data, this is often where the area of computational linguistics or natural language processing comes in. And then we'll use this machine learning framework to be able to predict output for the particular task or application that we're working with. So I'm going to be describing a number of different tasks and applications that we have developed over the years. And as I do, we're going to look at what data is available for learning for these different applications, and which features that we have yield good predictions. So over the years, we've been working with data and on tasks that extend from fact to fiction. And I've arranged them along a continuum here. At the top, we have data that is more objective in nature, scientific journal articles, news. And as we move down, we get to more subjective material. So in the middle, material that may have more opinion, personal views. And of course, when we get to the bottom, novels, we don't have fact at all. I've given several samples here of sentences that are drawn from these different genres. And this will give you an idea if we're developing programs to analyze and work with this data. They need to be able to adapt to the different kinds of language that's used. Now, for all of you, I think it's pretty easy to tell which sentences come from which resources. But when we're developing programs to deal with it, it can be a little more difficult. But let's try. I'm going to call out as we go through. We'll read it, and you can let me know which genre you think it comes from. So for the first one, we have devastating but yet amazing storm. IMBY, took me a while to figure out that acronym. Just some branches, tons of leaves. This surpasses any Big Daddy storm, should be called Big Mama. Okay, so what do you think? Scientific journal articles? No. News? Online discussion? Yeah, okay, so there we go. Second one, produced by a team of 26 scientists led by the University of New South Wales Climate Research Centre, the diagnosis convincingly proves that the effects of global warming have gotten worse in the last 3 years. Scientific journal articles? Yes. Hurricane Sandy churned about 290 miles off the mid-Atlantic coast Sunday night, with the National Hurricane Center reporting that the monster storm was expected to come ashore with near hurricane force winds and potentially life-threatening storm surge flooding. Okay, news. And then finally, what's the matter? I cried. A wreck close by. Novels. Okay, so one of the things you will notice is that in all of the examples, I've drawn from examples dealing with storms, and in fact, a lot of the work that we're doing now, we're looking at being able to deal with information about disasters. So I'm going to use that as a theme throughout the talk. Okay, now we can argue about which is more objective, news or scientific journal articles, but I'm going to put news at the top for the purposes, just the purposes of discussion, because news was the data that was available fairly early on in the natural language community, and we had a lot of labeled data. So in the early 1990s, there was a lot of work on collecting news and annotating it with labels for various natural language tasks, sometimes easier tasks like labeling words with part-of-speech tags. So really, the language field has been using these data science techniques for about 20 years now. And this use of news prompted us to begin our earlier work on summarization. We developed the system News Blaster, which every night scours the web, downloads articles, clusters them into events, and for each event generates a summary which describes that event. And so you see the one here for Hurricane Sandy. News Blaster has been running since about 2001, but this is a problem summarization that we continue to work on in various ways. Now, why is summarization hard? Well, it seems to require both interpretation of input text, that is, that we have to develop a system that can fully understand what is written, as well as systems that can generate paragraph summaries in output. And furthermore, since we're dealing with news or the web, the everyday world, we can't predict what those documents are going to be talking about. They could be on any topic and in any domain, and thus we have to be able to develop a system that can draw from these unrestricted topics in a robust way without failing. All of those things indicate that it's beyond the current state of the art in natural language processing, and so we have to develop a system that can operate without fully understanding the input text. And this has led many researchers in the summarization field to develop systems that use what's called sentence selection. They They take in an input article, and they'll select several sentences which they think are prominent, and then string them together and use that to form the output summary. But this leads to a number of problems. There can be misconceptions or confusions about what was actually intended. So in our approach, we do select sentences in order to avoid the problem of semantics, but then we edit them. So for example, in the example shown here, we have that the U.S. Geological Services said a strong earthquake hit off the coast. If we were to select that, we have a problem. What coast? Where did this happen? And so we edit the sentence to include modifiers which give us more information that hit off the Pacific coast of Guatemala. We also transform text by making it shorter or by fusing together phrases from different sentences. So, for example, this is part of the field of what's called text compression, and it's very useful when we have our mobile phones. We'd like to be able to get a short sentence that very quickly alerts us to the problems that are going on. So in the case of Hurricane Sandy, we had a crane that the high winds blew off one of the skyscrapers, and it was dangling over the streets of New York. And so nice if we could get a very short summary that warns us of that situation. Okay, so to carry out this task or application, we need a data set. And so we have a data set for compression. It's relatively small, about 3,000 sentence pairs. And you can treat it as a labeled data set for compression because it gives you a long sentence as input and a short sentence as output. And you can see that we want to maintain here the yellow and blue and put them together as a well-formed sentence in our output summary. So this is what we call text-to-text generation, and we model it as a structured prediction problem. Structured because we have different kinds of structures in input. The sentence and the parse trees, the syntactic structure that accompanies each one of the sentences. So our input is one or more sentences with these parse trees, and our output is a single sentence with a parse. And we do the work by using, by simultaneously reasoning over various kinds of decisions. Word choice, ordering of pairs of words within the sentence, and the syntactic structure of the sentence we're producing. So for the task of text compression, we get a single sentence as input, and as output, we get a sentence with the salient information. And you can see how this will work here, where we have what are called bigrams, the pairs of words like production closed, or at Ford, or for Christmas, which are all good normal phrases that we would hear. And as well the syntactic structure, which tells us this is the main verb and here's the subject and so forth. And so the words in yellow are kept, the grayed out words are dropped. We use the same framework for sentence fusion, and here our input is multiple sentences and our output is a single sentence with common information drawn from multiple sentences. To do this, we need to switch the data set, and we use one that was created from summarization evaluations, and we also change the features. Here we use features, for example, repetition across sentences. And we'll be able to take two sentences, like shown here, and then combine them by taking phrases from each one. So we would end up with a sentence 6 years later, independent booksellers' market share was 17%. And so in this way, we can generate summaries that are not just the sentences that were in our input. So what have we learned? Well, we've learned that if we use this approach, joint inference, and we have information about the structure, the syntactic structure, we can get a 5% increase in our metrics over the baseline. The baseline is here, and ours is up here. Going forward, we're looking at building a corpus from all this work on summarization, which we can use for future learning tasks. And right now, we're teaming with faculty in machine learning and in finance to be able to develop an approach where we can detect a new event in the news and predict its impact on the financial market. Of course, things can go wrong when we're using this. We're taking sentences that were written by people and we're changing them. And my favorite example is one when we were first developing Newsblaster and we were picked up by the press. So we had an article in the New York Times. And of course, all of these journalists wanted to find problems with our approach. And one of the problems that can happen is with family names in the news. You often have families that are famous and different ones appear. President Bush, for example, there were multiple President Bushes. The Clintons, there are now multiple Clintons. And so when we had this news event, we had a confusion in the system between the Queen Mother and Queen Elizabeth. And so we had, on the death of the Queen Mother in England, the system had Queen Elizabeth attending her own funeral. But my feeling is you have to try new approaches. Okay, so let me turn now to scientific journal articles. And we're dealing with a number of different kinds of journals. Nature is one of them. Science was another. So the first question we might ask is, how are scientific articles different? And if we just look at an image of an article, we can see several ways in which scientific articles are different from news. We have titles and authors. Authors come from different institutions. We have references, like the one you see at the top. Here we have an abstract. If we read further, we would see that we have citations to other authors. So we can exploit these kinds of differences in this data and make use of it for the tasks that we want to develop. We can build what are called citation networks. So if we look at the top, here are the more recent articles, and they refer back to articles which came before them. And if we trace all the way back, we would come back to the seminal article which spawned all of this work. If we look at the text, we will notice that the sentences within the articles have different functions. Rhetorical functions, and this is something that has been called argumentative zoning by Simone Teufel, who's one of the persons who we worked with on this. So, for example, with this sentence here, it presents the aim of the article, that is, what its contribution or its goal is. Here we present quantitative estimates of the global biological impacts of climate change. As I mentioned, we have citations, but we also have sentiment towards those citations, and we need to determine the length of the sentences which refer to them. So in this particular sequence, we have the articles are taking a negative viewpoint towards the economists. The approach of the economist takes a broader view. We argue that this approach misses biological important phenomena. So we want to exploit sentiment about what the authors feel about previous work. So we used this kind of information and this kinds of structure in the article for another task, to be able to predict in future years the scientific impact of a term or a document in the present. In this case, our input to the system was a term, like, for example, climate change or climate model, or a document. As part of the task, we were looking at extracting features from the full text of the scientific article, and our goal was to be able to predict in future years how prominent that term or document would be, how much impact it would have. So if we look at the chart shown here, where we have climate change in blue and climate model in green. And this is simply a time series of the frequency of these terms over multiple years. And we could see that if we looked at this feature alone, we would predict that climate change would have more impact in the future time, and climate model as a concept was going down. Our approach, we use, again, machine learning. Here we use logistic regression. We're not doing work on the machine learning itself. We use existing tools. And we're exploring the different features that we can use. So we explored the use of metadata features like the citation network, which you saw earlier. We also looked at author collaboration networks, that is, who worked with who. So if we look at a particular author and whether his work has prominence, how many authors did he collaborate with? And then we also looked at features that we could draw from the text. That is, what is the function of each sentence in the input? Is it the aim of the article? Is it background? Does it refer to other work? Or is it the methods and so forth? The citation sentiment, what does the authors feel about previous work? We also looked at the primary concepts that were talked about in the article and relations between them. As data, we had 4 million full-text Elsevier journal articles. In addition, we had a much larger collection of metadata information which came from the Web of Science. So these were metadata records contains information about authors and citations and so forth. We were developing this in a way that we could apply it to different disciplines, so not focused on a particular field. And our articles drew from the medical field, chemistry, biology, and computer science. And for training, we had what was called a ground truth function, so that if we had articles from an earlier period, we could use this function to tell us what in fact was true. So in our experiments, a lot of people had looked previously at metadata features, that is, who cited who and author collaboration and so forth. We wanted to see how helpful was it to have the features that were drawn from the full text. Could these be used to predict impact? And so we carried out some experiments with selected articles from Elsevier and their counterparts in the Web of Science. So in other words, not the full 48 million. We wanted to have a fair comparison between the two, so to have exactly the same articles. What have we learned? Well, if we look at our output, we see from the blue line that text features alone outperformed metadata features alone. Here we have, we were using as training data, or we were using as our reference year 2003, and from whatever we could see in 2003, we wanted to predict how much impact a term would have in any of the years from 2004 to 2007. And we looked at correlation with ground truth. And here, as I said, you can see that the text features alone really outperform the metadata features. That was somewhat surprising to us. We did see that if you use both together, the text and the metadata, you did have value. So the metadata did add value, and you did get some improvement. So we thought, well, maybe this was an unfair comparison because there's actually far more information in the metadata than in the text articles. We had a much larger collection. And so perhaps we should look at all of Web of Science, the full 48 million articles, and the reduced set of Elsevier. So what did we learn here? You can see that we still have an improvement of text-only features over metadata. This was surprising to us. Although metadata performed better, it still did not meet the text data. And of course, with both, we still got an improvement. Okay, so let me turn now to online discussion forums. And our question here was, can we use data like Twitter, Facebook, although Facebook is not readily available, but or various kinds of online discussion to answer questions that people may have. And we reasoned that this could actually be quite useful in the case of disaster because more information becomes available quicker on these sources. So how is online discussion different from the genres of news and scientific journal articles? Well, it provides unedited perspectives from the everyday person. It's often in the form of dialogue, so you're often seeing people posting and other people responding. It definitely contains opinions, viewpoints, emotion, and as we all know, the language of social media is not the language of news, so we have to be prepared to deal with that. We were looking initially at questions about events. So we wondered if we asked questions, could we develop a system that could provide answers? And we were looking at sort of open-ended questions, like what is the effect of Hurricane Sandy on New York City? And from the various systems that we were developing, this is an answer I particularly liked. It's in no way representative of what the system can do, but it gives you an idea of the power of drawing on this kind of data. So here we have, it's dark, there is minor price gouging, there are restaurants selling hot food through their bay windows. The police are doing an amazing job with traffic concerns and directing traffic. And now, at this point in time, after Hurricane Sandy hit, the whole southern half of Manhattan was dark. There was no electricity. And if you ventured into the dark half of New York, you came across things that looked like fires, people gathering around fires. But what it was many stores set up these recharging stations for people to recharge their electronics. So this answer really gives a real picture of what it looked like at that point in time. It's hard, though, to generate answers to questions about events. We have problems like there's no word overlap between the words in the question and the words in the response. So nowhere in the response do you see the word effect, Hurricane Sandy, or New York City. And yet this is an answer that is definitely relevant to that question. So again, we used a machine learning point of view. We started off thinking, well, we would generate some annotated data, some labeled data, which for various questions, we'd have a question and we would label which sentences were relevant as an answer to the question and which were not, and we would learn from that data. So we used crowdsourcing to do this. We took a query and we generated through information retrieval documents that were relevant, and for each sentence in a relevant document, we posted it on Amazon Mechanical Turk, the question and the sentence, and asked the Turkers to indicate whether it was relevant to the question or not. Now, we used Mechanical Turk quite a bit up to this point in time, and usually we're able to generate a labeled data set in a couple of hours, very quick. But this time it took weeks. 3 weeks, and we still had very little data. And the reason is that many of the sentences in these documents were not relevant. So there was so much that had to be annotated as not relevant before we got anything positive. So we ended up with this very small amount of manually annotated seed data. But then we realized, well, actually, we have a lot of data that we've collected automatically. We had Newsblaster, which had been running for over 9 years, and this generated huge amounts of data which we could exploit for our task. So we took 9 years of unlabeled data from Newsblaster, and we reasoned that the headline of the summary serves really as a query about the event that's being reported on. The summary itself contains many sentences that are relevant to the event and a small number of sentences that are irrelevant. So we could use that as a sort of noisy training data. We also drew on question-answer pairs from various discussion forums, Yahoo Answers and Quora. Then we could use this data in combination to predict a relevant sentence, and we use semi-supervised learning for this task. We use co-training, so we had multiple very simple classifiers which we trained on the seed data. They could use simple word overlap or overlap of names, but we also looked at features based on semantic relatedness. We're now moving that approach from answering questions about events to monitoring events over time. So as input, we're taking streaming data that would come from news, social media, or web page. And as output, so for our task, at every hour, we want to update with what's new. So as opposed to a general summary, just what's different. So again, we could imagine October 28th, 2012, this is when Hurricane Sandy was approaching. We're looking at our computer to see what's happening, and we get a lot of information and a lot of it repetitive. Instead, what we'd like is to be able to do this update. And to do this, again, we need data. We participated in an evaluation that was set up by NIST, which is a standards board in the US, but the evaluation is run internationally. This was a corpus that they collected, which was an hourly web crawl over a 2-year period from 2011 to 2013, and we had 16 terabytes of data from that. We also use training data from Wikipedia, where we have articles on various kinds of disaster. So this is what it looked like, and I don't expect any of you to read it. The point is, it's a lot. If we look more closely within it, we can see that some of the sentences are relevant. So here's a sentence from the Tsunami Warning Center about the earthquake, which obviously we would want to see. Other sentences are not relevant. They happen to come from the discussion. And other sentences are what we would call junk. We're dealing with web pages, and a lot of the content on web pages is just additional formatting that comes with it, or advertising and so forth. So instead, what we want for that kind of input is a system output like shown here, where perhaps in the first hour we hear that the earthquake has hit, where it is hit, and what cities are affected, as well as the magnitude and the actual location. So our approach is that we want to be able to predict salience for the input sentences, that is how relevant they are, just like we did when we were answering questions. And since we're focusing on disasters, we use disaster-specific features for predicting that salience. We want to remove redundant sentences, so when we're in hour 2 or hour 3, we don't want to report what we already reported in hour 1. And we still have a lot of information, so we want to cluster and select only example sentences. To predict salience, we have a number of different features that we experimented, some basic level sentence features, and these can help us in determining which are the sort of sentences we want to avoid. So for example, if we look at the number of capitalized words in the sentence, the high sentence salience and the medium salient sentences have fewer of them, while the low salient sentences have a lot. So it allows us to weed out some of the junk that we're seeing. If we look at what are called hypernyms, so this is semantic information, an earthquake is a type of disaster. So if we see disaster, which is a hypernym of earthquake, we know that this sentence is likely to be more relevant. So again, another feature which helps us in the task. I apologize because it's going to get, not everybody I know knows about language models, but language models are models that we build that tell us how likely it is in a given corpus to see certain pairs of words or 3 words in a row or 4 words in a row. And it gives us an idea of how typical a sentence is. We can score it by a language model. So we used 2 different language models, one which came from generic news, and we used 10 years of the AP and New York Times articles. And other language models, we had one for each type of disaster that we might expect to see. So we had an earthquake language model, a hurricane language model, and so forth. And we built these based on disaster-related Wikipedia articles. And again, these could help us in detecting which sentences were more salient. The generic news corpus helped us define sentences that are more grammatical, were more typical in regular news. And the domain-specific one would help us find sentences that are we would expect be more likely to see when talking about a particular disaster like an earthquake. And then we had geographic features, so we looked at location, whether the sentence mentioned a particular location, and we used a distance between the location and the mean distance to the event, again, as a feature. So we have 2. Nicaragua was closer to the event than Mexico City. And then finally, we used temporal features, which would indicate how different the words are that we're seeing now from what we saw the hour previously. So our goal with all of this is to be able to take an event, streaming data on the event, and to be able to identify sub-events. So initially, news about Hurricane Sandy, but then to be able to identify that a sub-event, the blackout in Manhattan occurred, the Breezy Point fire, a fire occurred, and the New York City subway flooded. So what have we learned here? Well, we participated in this evaluation. The average score in the evaluation is shown at the top. We ran several different systems, and one of the things that we learned was that our salience predictions helped increase precision. And I should mention that their metrics are not exactly precision. They compute a norm and then how far away you are from the norm. So they look low, but they're not so low as they look. In fact, our system was the best performing in the evaluation. But we also saw that our method for penalizing redundancy didn't work as well as we thought it would. When we penalized according to our various features for redundancy, we removed too many important facts. So going forward, we're interested in looking at other kinds of questions that we really would expect to find when we're looking at online discussion forums. Questions about how people feel. What is the reaction to Hurricane Sandy? Which would have sort of emotion in it. As many others, I'm still speechless at the widespread damage. Questions about hypothesis, what people are thinking might happen. How do people expect Sandy to impact the election? I can only imagine how this will make the nightmare of voting in densely populated areas even worse. And then other kinds of hypotheticals. What will you do if you've lost your house? Or how does it feel like to be in a hurricane? So I'm going to move on now to our work on personal narrative. And I've used as an example the autobiography of Malcolm X. Now, we aren't dealing with anything of length like that, but I use it to give you an idea of the compelling nature of the stories that we're looking for. We're really looking at stories which convey life and death information. So how is personal narrative different from the different kinds of language that we've looked at so far? First, we expect to have a coherent telling of a story. We want to hear the whole story. We expect to have a very compelling component, this life and death situation. The narrative is monologue, unlike online discussion forums. But like online discussion forums, it's a very informal language, so unlike news. This is an example of the kind of narrative that we're looking at being able to identify and pull to the forward as an example of personal experience that happened during a disaster that people might like to read about. And we're following the theory of sociolinguist William Labov at Penn in being able to identify components of the story. So we notice at the beginning we have a background. We were sitting down to a late dinner on Monday night when the storm was supposed to hit. Next, we have what Labov calls complicating actions, a series of actions that are causally related that lead to the climax of the story. So we get, by 10 p.m., the skies lit up in a purple and blue brilliance, and the power started to go out here and there. That's when I noticed neighbors across the street running out of their houses and fire trucks racing down the block, and so forth, until we get to the final part, which is what we call the most reportable event. And here is the part of the story which gives this sort of compelling action. We're looking for relatively short narratives on the internet which can convey this. So here, my husband went to grab the pump. He went upstairs to get a tool, and in those few seconds, ocean waves broke the steel door lock and flooded the basement 6 feet high in minutes. So the question that we pose for ourselves is, can we learn this kind of narrative structure so we can identify good narratives on the web? We want to be able to automatically label every narrative clause within the story with the element of narrative structure. And for our initial experiment, we looked at, could we reliably annotate the complicating action only? We had a very small corpus, very small data set, 20 oral narratives, which we took from Labov of personal experience, and you can see a breakdown here of the kinds of the number of clauses of each. Complicating action had the most at 573, but the total was still relatively small at 1,200. We used logistic regression for our machine learning and a balanced training set with a testing set which reflected what was happening in our data. And we looked at several different kinds of features. We looked at features, narrative features that were proposed by Labov. For example, the position in the narrative or how long the narrative was. We also looked at features that people have used in the world of NLP for discourse, be able to analyze how clauses hang together. So what have we learned here? This is very early work, but we were able to see an improvement in our metric over a baseline where we only looked at the words. We learned that the narrative features from Labov were useful. They performed better, actually, than the discourse features. And in our current work, which actually I'm very excited about, but it's still very new, we're now looking at, can we automatically identify that part of the story which is the most reportable event? And we'd like to do it without really looking at the words. And we clearly, data was a problem. We didn't have much with our manually labeled data, so we're augmenting the data with Reddit stories. Now we can get thousands and thousands of these Reddit stories, and we're using various heuristics with the online comments to be able to identify which is the most reportable event. Okay, so finally, let's turn to look at the work on novels. And of course, this is quite different from the previous work. We looked at 19th century novels like David Copperfield. And if you look at the kind of language that you have in novels, you can again see quite a bit of difference from what came before. It was broad day, 8 or 9 o'clock, the storm raging in lieu of the batteries, and someone knocking and calling at my door. "What is the matter?" I cried. "A wreck close by." I sprung out of bed and asked, "What wreck?" "A schooner from Spain or Portugal laden with fruit and wine." And so we can see that what we have here is heavily dialogue. So we used a corpus of 19th century novels. These were freely available for us to use. We had about 60 novels, and we worked with a professor from comparative literature, who's actually the chair of the department, in developing a balanced corpus across different genres and different authors. And what we looked at was whether we could use this corpus and automated techniques to provide evidence either for or against literary theory. And to do this, we used social network extraction from this corpus of 19th century British literature, where the social network was based on the conversation in the novels. To identify conversation, we used a method based on quoted speech, where we could identify who talks to whom, and then from this extract graph features that could evaluate the hypotheses from comparative literature. Previously, people had looked at various kinds of hypotheses, but they had done a lot of it with manually looking at it, which meant they were very limited in the number of novels that they could look at. So one of the hypotheses that we tested in the 19th century, over the course of the century, there was movement from the country to the city, and during the course of that movement, we developed much larger collections of characters within each novel. And the hypothesis was that as this move took place, and we got larger conversational networks with many more people, that they tended to be less connected, that people grew apart from each other. So we have two people from comparative literature, and their quotes. Franco Moretti, who says, at 10 or 20 characters, it's possible to include distant and openly hostile groups. And Terry Eagleton, who said, in a large community, most of our encounters consist of seeing rather than speaking, glimpsing each other as objects rather than conversing as fellow subjects. So these represent the theory that we were evaluating, and we wanted to see whether we could show empirically that conversational networks with fewer people are more closely connected. So to construct the social network, our nodes were equivalent to people who said something. To do this, we had to do what's called quote attribution, that is, in the text, associate names of characters with what they were saying. Edges represent people who are talking to each other, and we used a very simple heuristic to determine who was talking to who, quote adjacency. And you'll know often in novels you have just blocks of quoted text with alternating people talking to each other. The edge weight was set to the share of the detected conversation, and this approach worked quite well for precision. What we got was when we found people who talked to each other, 95% of the time was correct. But our recall was low. We could only get about half of the conversational partners. Then we looked at the impact of network size. So we looked at various metrics that are used with social network and compared them with the theory. So as the number of named characters increases in the novel, we would expect to find the same or less total speech. And we found this with a weak yes. The normalized number of quotes was flat, remained flat. We would expect to find a less lopsided distribution of quotes among the speakers, and we found that was true. The share of the quotes by the top 3 speakers decreases. But as the number of named characters increases, we would expect to find that the network has lower density. That is, as fewer conversational partners as percentage of the population of the entire network. And we found this not to be true. We found larger networks are more connected than smaller networks. We would expect to find same or fewer cliques, that is, small groups of people who talk to each other a lot. And we found this not to be true. We found the rate of 3-click increases, so larger networks form cliques more often. We thought, well, maybe we shouldn't be looking at characters. Maybe we should be looking at, excuse me, at people who are actually speaking. So we restricted it to speakers. We would expect here to find less overall dialogue again, this glimpsing rather than speaking. And we found this not to be the case. We found an increase. Larger networks are actually more talkative. And we would also expect to find lower density. That is, speakers talk to fewer of their neighbors. And again, we found this not to be true. In larger networks, people know more of their neighbors. We did find an alternative explanation, which came from text perspective. This dominated the shape of the network. So for third-person tellings, we saw significant increases in every one of the metrics that we had looked at. And so our hypothesis is that first-person narrators are not privy to the other characters' conversations with each other, and this is what changes the shape. So if we look at some example networks, we can see this. This is a network that is formed from a novel, Jane Austen, Persuasion, which is a third-person narrative, and we can see that the characters are relatively connected. The main character, Anne, is slightly larger than the others. If we move to what's called a close third, this novel is told from the perspective of Robert, and we can see the change in the shape. We see a lot of who Robert talks to, but very little of who the other characters talk to. And then finally, if we look at Dickens' David Copperfield, which is told from the first-person narrative, we can see what we call the great eye of Dickens. Everything is centered around the narrator. So what have we learned here? Well, we have learned that we can extract high-precision conversational networks from literature, and we think the time is right for exploring analysis of literature. We have thought a lot about what we might have overlooked because our analysis provided evidence against theories from comparative literature. So we're beginning looking at other kinds of things that we can extract from text. We only extracted quoted speech. What if we can extract information about other kinds of social interactions? And in fact, one of my colleagues works exactly on this. So he can look at both bidirectional interactions like speaking and unidirectional interactions like seeing or glimpsing. And so we're looking at the difference between the percentage of these kind of interactions that can occur, social networks based on those, and we're also looking at how they change over the course of the novel, so not just a static view of it overall. So we are looking at how we can put all of these together. I am not including novels in our integration. And our view here, and this is a mock-up of where we're going, is that we might create a presentation that looks something like this, where we have a timeline and we have a spatial view of the area in which we have a disaster. Here we would have first the information Sunday, 12 a.m. at Breezy Point. He went upstairs to get a tool, and in those few seconds, ocean waves broke the steel door lock and flooded the basement. To the second night, Tuesday, 8 p.m., New York City. It's dark, there's minor price gouging, there are restaurants selling hot food, and so forth. To several days later, discussion on social media, where we have discussion about the elections, postponing the vote. And then finally, a month later, to be able to look at the impact in scientific publications on climate change. So as we move forward, given the fact that we're situated within the Data Science Institute and we have access to various interdisciplinary connections, we're beginning to look at how we can integrate what we see as the lens of the media on a disaster with scientific knowledge about what has happened in order to be able to better predict the unfolding impact of disaster and to allow social media to feed into models of resilience within the city. So I have to close and mention my PhD students who have, of course, done most of the work that I've reported about today. These are my current PhD students. This work was done over quite a few periods of years, so it draws on the work of my past PhD students as well, one of whom introduced me at the beginning of this talk. And so I'll close with the thank you.
Before I go into questions, if Kathy doesn't mind, I'll do a little bit of targeted advertising. I'm teaching the course on data analytics on text and speech this semester. It's open to everybody, no prerequisite. And UG, PG. If you want to learn more about what Kathy was talking about, things like language model, information retrieval, text summarization, all that. So we go through that in my class. It's been half semester already, or you can still sit in. So that's a little bit advertising. Other than that, any questions, comments? Oh, in front. May.
Yeah, very interesting. I learned a lot. I'm not in your field, as you know, but I have a pressing question. As the term, since you're in language, the term big data. It's other than meaning a lot of data. Is there any meaning to it, and why? Why big?
Well, let's see. So what quantity, at what number would you reach where you had to say you were at big data rather than just any use of data-driven methods? The thing is, I think right now we have very large quantities of data available on the web, so these streaming environments that we're talking about. Often the kind of big data that you have available, you only have available in what I would call the real world. And, for example, in companies, we're working right now with Bloomberg, which I think, when we have 16, I mentioned 16 terabytes worth of data in our streaming setting. They download and process 1 million news articles per minute. So it gives you an idea of the difference between the two. When we have the Internet of Things, so all of the sensors that are connected, and again, streaming data that is collected every second. I mean, these are all cases where we're moving from a world where we had data and we could make use of it, but now we have terabytes worth of data and we can look at what we can do with it.
Right, but the term big data is kind of like a scientific field.
Is it a scientific?
Yeah, or technology. But we all working, doing research, we're all dealing with big data.
No, I don't think it's a scientific field. I think it just refers to the fact that we now have huge amounts of data available. So it's not a particular field. Data science is a particular discipline and approach to how you would use this big data. And data science comes about because we have so much more of it now. Data science refers to the use of statistical inference, machine learning approaches to making predictions from that big data.
So you actually mentioned machine learning quite a few times. What sort of machine learning techniques are you?
Well, in general, we're not working on machine learning itself and new techniques for machine learning. So we experiment with, we take an experimental point of view. We try different techniques that are out there and we see what performs best. Occasionally I have, given the kind of problem that we're working on, we do look at developing new inference techniques with, for the data. So for example, the work on structured prediction, the PhD student who worked on that was looking at different kinds, how to do approximate methods, how to do fast learning, and different representations for use. But we've experimented with support vector machines. I have tasks in which that is best. Logistic regression is often quite useful. We've used HMMs, CRFs. I tend not to use so much techniques like naive Bayes. My group doesn't use in particular, but many groups do use latent Dirichlet analysis. So yeah, there are a variety of different approaches you can use.
Kathy, a tremendously interesting talk, full of insights in lots of things. I have several questions. I'll ask one. In the very beginning, when you talk about news articles and parsing sentences to extract the keywords and then sometimes combining sentences, do you have some algorithm for judging, as you do this, what is the right amount of information that comes out of it? You talk later, in a later context, about a statistical analysis that says maybe you've cut out too many redundancies. How do you calibrate your parsing of sentences?
So in that first one, we calibrate it entirely by the data that we have. So we have this set of training data, which I showed where we had long sentences and short sentences. And once we have implemented our algorithm and we can generate the short sentences from the long sentences, so we take this data and we divide it into a portion that is used for training and a portion that is used for testing. And we run, once we have our developed system, on the testing portion, and then we want to measure our output, how close it is to the short sentence in the training data of the output. And there again, we had to look at different kinds of metrics that we might use, but we look at things like how many of the words did we capture or did we miss in our output. We look at how many of the syntactic, like the dependency relations, did we capture or did we miss in our output. That's one way. In summarization as a whole, there have been evaluations where we take human summaries and machine-generated summaries and make a comparison against them. There's a lot of complications in doing that because there are many ways you could write a good summary. So we have to think about things like how many summaries of the same input article do we have to have, and we compare our generated output against this multiple set of gold standards rather than just against one. If we compared just against one, we'd run into problems.
The two questions. One is on the first part you mentioned. Once you reduce the sentence structure, then the next thing is how to visualize the data. For example, we went with several colleagues, went to Security Future Commissions, Hong Kong. They are very interested in knowing, say, the government announced certain initiative, or the stock markets have some new information, how the sentiment from the public sector, from company or individual investors coming in. So then if the data scientists can develop very quick information, then visualize that back in a more like real time. And clearly this information is very important. So what you have mentioned today, actually I think is a very important part of the whole solutions. The other is whether your center has also have efforts in visualize the data once you recompile them.
Yeah, so yeah, that's, I mean, data visualization is a whole area within data science. At Columbia, we find it in different parts of the university. So there are people in statistics who do data visualization. We also have people in the Graduate School of Architecture. I find the work so interesting. I mean, they take very practical applications like the City Bike program in New York, which has made bikes available, but you need to know where they are and where they aren't, and to give a visualization to show where they are. So very practical, but it is a work of art. It is beautiful, the visualization. And then we also have visualization in journalism. So for the particular problem that you're asking about, where you have sentiment towards, let's say, particular companies, and you want to visualize it as it comes in, I could imagine that as a pairing between people who work in natural language processing and do the analysis of the sentiment and the documents, and people who work on visualization who can show it in a way that's meaningful.
The second question is more that the algorithm you mentioned earlier in parsing the sentence structures may be used to adopted by Chinese language. So in the sense that the platform is generic enough.
First question, if I may, sorry to inject. We have used tools for students to analyze the sentiments contained in text and actually plot it in a temporal signal. So you can imagine it will look like a signal of positive and negative words. And even Google search online, they have tools that students can just use to visualize. Sure? Yeah. By the way, after this, is there any student who would like to ask a question?
Really interesting, Kathy. Remind me to discuss with you possibly applying our semantic-based MT, machine translation evaluation metric, to that question about how to measure summarization.
Oh, yeah, that's a
cool.
Yeah, that's a good.
But I just want to make a couple of comments regarding, because I think a lot of the people in the room here are coming from a data science side, but not understanding the perspective from a natural language, statistical natural language, and computational language. You know, a lot of these methods, the field, data science, big data, whatever, from our point of view, there's a separation between applying existing methods versus developing new methods. And data science a lot of that is about developing methods that you can use to analyze the data. Tremendous amount of that came out of this research community. For example, hidden Markov models came out of people working on spoken language. Conditional random fields, CRFs also, these are widely used in machine learning. They're driven by work in this field. And the definition of big has evolved over the last 20-some years. Back in the early 90s, when the workshop in very large corporate started, very large meant a million words. And of course, with Moore's law, we continue to follow that curve to the 16 terabytes that Kathy is talking about today. So I think it's really important to focus on what kinds of things the machine learning, the data analytics can learn by themselves. We are looking right now at unsupervised learning of the structural relations between the structure of languages. What is the structure of English, what is the structure of Chinese, and what is the structure of the relationships between them? That's a lot harder than feeding a lot of features into a flat classifier. And I think that's where data science as a whole has to go, and computational linguistics in particular has a tremendous amount to contribute.
Oh, thanks for the talk. I have a question about, in the second point where you talked about the online forum data, the corpus from the forums, the task here was question answering, right? Do you use the answer from the training corpus? I mean, do you select answer that already exists there, or do you generate the answer?
So the particular one that I showed you was generated by a system that selected chunks of text from the input. We didn't use answers from the training data, but it used a sentence selection approach, and it selected more than one sentence. So that's why that one came out looking particularly good. We have not looked there at some of the other approaches that we used earlier.
So So when you select, so you have first to select few sentences, right? Do you score them somehow? Like, what are the criteria for scoring the adequate sentences?
We do score them based on a variety of different features that we use and how well the answer matches those features.
All right. How about the sentence of the output answer? How do you define that? Is it random or size of the output sentence, the answer?
In how big
long
is
it
the
is,
answer?
or
to be honest, I think we've experimented with different techniques. I'm not sure what we were using there at that point. We might use a threshold for how relevant it is and grow the answer until we meet that, we cross that threshold, and further sentences are less relevant.
Sometimes people use compression rate, right? The control for the compression, summarization. Yes?
You mentioned in all your tasks you have like a bunch of features that you extracted, and given the diversity of these tasks, I was wondering if you've observed some similarities in trends as to what kind of features typically help. So in case you need to transfer some infrastructure or some engineering to, let's say, a newer kind of learning problem on similarly large-scale data sets, like, do you have any lessons that you've learned from?
Well, if all the features were the same for each task, then, we'd be done. There'd be no point in sort of going ahead. Part of the interest, I think, is in discovering for us, I think that's part of the interest, is in looking at what features are helpful. And certainly from the point of view of kind of, more linguistic analysis, which, despite the move to statistical approaches, I am still interested in. To a certain, in some cases we try to move away from using the words because we would be training based on, what we have. In other cases, we find the words or some subset of the words quite useful in telling us content. Often syntactic features are quite helpful. So, part of speech or whether we have a subject-verb relation or verb-object is very helpful in the task. But other than that, it can really vary, I think, from one to another.
Thanks a lot. And a follow-up question is, what is your opinion of, let's say, deep learning style models with just learn embeddings and could potentially incorporate all the features that you talked about? Do you see them as actually being relevant for the kind of tasks that you've worked on in the future?
So I think I have to give a no comment as a reply. We have not experimented with deep neural learning yet. One of my students is experimenting with word embeddings. They are in some ways very similar to work that has been done previously on, distributional semantics or even early work that Pascal did on context vectors. So, I guess I worry, as always, about hype. That would be part of my reaction. But as I said, I haven't tried them myself, and I have to have an open, or my students are only beginning to try them, so I have to have an open mind.
So in our group, Dario has tried to compare deep learning to CRF and has not shown, any advantage of the conditional random fields in the text mining. Not yet. We have not yet seen.
Kathy, this comes up in the context of the question just asked, and Kai's mention on the structure of language. So you talked about the narrative and extracting the components of a narrative, and my paraphrasing, which may not be correct, is that you're trying to extract the information out of text. But to go back to the way that some of us were taught in analyzing literature, whether English or Chinese, what struck me was in that text, in the complication aspect, there were these words blue and purple brilliant skies. So my question is, and that just struck me, it was not something that was necessarily part of the core of the information, but sometimes we're taught that certain conjunctions of words or certain descriptors make a passage all the more memorable. Maybe it's literary, maybe it's just the way we have of communicating. How much, so maybe that's the old analysis of language and of text, and yours is the new analysis. What role does that old analysis and the new analysis have in the new analysis? I mean, where do you, might you use things where people talk about colors or smells or words that are deliberately used to make an impact on a reader in the more conventional sense?
So I'll answer in two ways. One is that that kind of, what we might think is old style, but it doesn't have to be old style. It can come from, I would say, a more, I want to say theoretical, but it would be a more linguistic or comparative literature point of view, a literary point of view of what makes something good or not. And those kinds of things are really our inspiration, in terms of how might we experiment with different kinds of features. So if we looked at some of these things like alliteration, for example, or the use of unusual colors, that might be one inspiration in terms of what kind of features to apply. We've started with structure because it's easiest. It's the large structure of the narrative. It's easier. But I will give a little preview of the work on identifying the most reportable event, which I am finding very interesting, and the student who is working on it is just doing remarkable work. My first thought on the most reportable event is, well, it's compelling, it's life and death. Shouldn't we be looking at the words? We should see like a lot of blood and guts and gore, and this should tell us that that's, that we have found it. But in fact, if we're just looking at the words and that kind of thing, we probably are limiting ourselves in terms of topic. There may be many different kinds of most reportable events and so forth. So the student who is working on it has looked at, just as we talk about the complicating action leading to this climatic point in the story, has looked at a rise and fall in emotion, for example, how strong the words are. We would expect to find words that are much more active as we get towards that most reportable event. Similarly, she's looked at a quantitative view of imagery, how concrete are the words and how much do they evoke an image. And she is creating a set of features that are splines based on a curve according to these different views on emotional content that's conveyed and how it changes, and imagery and various other things. So if the paper gets accepted, you can hear more. I'm waiting to hear.
I have one short question, maybe. Are most of the headline in the news media now generated by machines? So we won't see a headline like high school dropouts cut in half, that's that kind of thing that have double meaning.
Oh, we love those headlines for our NLP classes. They're great. I don't think most headlines are generated by machines right now, but many stories, and it depends on what kinds of stories are generated by machines. There was just an article in the New York Times a couple days ago which asked if you could tell the difference between the human-generated news and the computer-generated news, but of course it still tends to be on the somewhat stereotypical topics like sports, the market. California uses an earthquake-generating report system so they can get a report of the earthquake into the news faster than they could if it had to be written by hand. So there.
My machine learning class tested
Yes.
on that article.
Oh, yeah?
On that quiz. And they couldn't tell the difference more than 50-50.
Uh-huh. So, but I think there's still a lot that's written manually.
I have just a curiosity. You have studied, obviously, Sandy very much as a case study. You have all these timelines. Did your system actually come up with on the timeline, do you have Mitt Romney got pissed off by Christie hugging, Obama? Was that part of your timeline?
I can't answer you on that one. I don't know, but I'll bring it back to the system and we can test it out and see whether we get it as output or not.
Okay, so afterwards we have a tea reception upstairs, right, on the 5th floor, because the outside lobby is under maintenance. So please come and you can talk to Kathy more, talk to professors here who are in data sciences to have more interaction.
Okay, so thank you very much, and thank you for inviting me here to talk.